Topology of real numbers part 2. I'll be discussing theorems on neighborhood here. The very first theorem, it states that any superset of a neighborhood of a point is also neighborhood of that point. Means there is a point, we have found the neighborhood of that point. Then once we have found a neighborhood, any other set which is a superset of that neighborhood will also be the neighborhood of that point. To understand this, suppose P is any point, then the open interval containing P is contained in the neighborhood. Suppose it is contained in a set N, which is a neighborhood of P. And now we are saying any superset of N will also be the neighborhood of P. But obvious, because the open interval containing P is also now contained in M too. So M will also work as a neighborhood. So how to write this? Let N be any neighborhood of point P. Then by definition of neighborhood, there exists epsilon positive such that the open interval P minus epsilon P plus epsilon is a subset of N. This is the definition of neighborhood. Now we are saying M is any superset of N. If M is any superset of N, then M contains N, or rather we should say N is contained in M. Combining equation 1 and 2, we get the open interval that contains P is also contained in M. See, to avoid the ambiguity, I am writing epsilon this way so that it should look different than belongs. I'll be writing epsilon this way now so that I can differentiate between epsilon and belong. P belongings to P minus epsilon P plus epsilon is now contained in M. So again, by saying with the definition of neighborhood, we say M is neighborhood of P. So we have chosen any superset of N which is also working as neighborhood. So whatever superset we will be taking of a neighborhood will also work as the neighborhood, hence the result. Now theorem 2 states intersection of two neighborhoods of a point will also work as neighborhood of that point. First, this is the definition of neighborhood, that any open interval containing X will be contained in N, which will be the neighborhood of X. So now we are discussing two neighborhoods of one point. So suppose for neighborhood N1 I am getting epsilon 1 as radius to cover X, and for neighborhood N2 I am getting the bit higher radius epsilon 2, X minus epsilon 2, X plus epsilon 2, an open interval contained in N2. So whichever radius will be minimum, so here by looking at this picture we can say epsilon 1 is a minimum radius of 2, epsilon 1 and epsilon 2. So the minimum one will work as open interval for both, right? So we'll be considering the minimum radius to discuss intersection part, because the minimum radius interval X minus epsilon 1 X plus epsilon 1 will be contained in both and hence contained in intersection. So how to write this? Let N1 and N2 be the two neighborhoods of a point X, then there exists epsilon 1 and epsilon 2 such that by definition of neighborhood we can say these intervals containing X are contained in N1 and N2 respectively. See here itself you can take the same epsilon, but if you take the same radii to cover in both the neighborhoods, then there is nothing to prove. So we have chosen the different epsilon. Now considering epsilon as the minimum value of epsilon and epsilon 1 and epsilon 2. So the minimum value will be contained in both, because if it is epsilon 1 it will be the subset of epsilon 1 also, and it will be the subset of epsilon 2 also, because we have chosen the minimum. So combining equation 1 and 3, we will be saying X minus epsilon X plus epsilon is a subset of N1, And by combining second and fourth, we'll be saying x minus epsilon, x plus epsilon interval is contained in N2. So this is the common interval contained in both, and hence it is contained in intersection. So we have found an interval, an open interval containing x as a subset of N1 intersection N2. So by definition of neighborhood, I can say here N1 intersection N2 is working as neighborhood of x. So we have chosen two different neighborhoods, and now we are able to say their intersection is also neighborhoods of that particular point, hence the result. Next is a set A is neighborhood of x if and only if there exists a positive integer n such that x minus 1 by n, x plus 1 by n subset of A. See, the theorem is if and only if, means we need to prove the result both ways. The converse part is very easy because x minus 1 by n, x plus 1 by n is a subset of A, means it's clearly stating A is neighborhood of x by considering 1 by n as epsilon. So to prove the direct part, let A be the neighborhood of x. We need to prove x minus 1 by n, x plus 1 by n subset of A for n being natural number. So first of all, I'm writing the definition of neighborhood. By definition of neighborhood, I can say x minus epsilon, x plus epsilon is a subset of A. And now since epsilon is positive, 1 by epsilon exists and is a real number. And for any real number, which is here I'm talking about 1 by epsilon, there is always existing a positive integer, that is a natural number, which is greater than that particular real number and greater than 1 by epsilon. This is Archimedean property of real numbers. Now you can understand very clearly by taking example. Suppose 2.3 is a real number. 3 is a positive integer which is greater than 2.3. If you choose 1000.123 as a real number, 1001 will be existing as natural number greater than that. So whichever real number you choose, there exists always a natural number which is greater than that real number. That is n greater than 1 by epsilon, which can state 1 by n is less than epsilon and minus 1 by n is greater than minus epsilon. Adding x to both inequalities, we'll be getting x plus 1 by n less than x plus epsilon, and with the second one I'll be getting x minus epsilon is less than x minus 1 by n. So that means the interval x minus 1 by n, x plus 1 by n is totally contained in x minus epsilon, x plus epsilon. I'll explain this as geometrically also. First, combining equation 1 and 2, I can say that x minus 1 by n, x plus 1 by n is a subset of A, which proves the direct part of the theorem. Now to understand the concept, x minus 1 by n and x plus 1 by n is contained in x minus epsilon, x plus 1 by n. X plus 1 by n is less than x plus epsilon, so it should lie here. And x minus 1 by n is greater than x minus epsilon, so it should lie here. So the interval with x minus 1 by n, x plus 1 by n is contained in totally x minus epsilon, x plus epsilon. Now the converse part, if there exists a positive integer satisfying this criteria that x minus 1 by n, x plus 1 by n open interval is contained in A, then it is clearly satisfying the definition of neighborhood, that x contained in this open interval subset of A, that means A is a neighborhood of x, which proves the converse part, hence the result.